Hey all, this is Alan with Bothell STEM Coach, and today we are going to continue on with some more AP Physics 1 rotation questions. So let's take a look at this one. As usual, I suggest you pause the video, attempt to do the problem on your own, and come back after you've watched the video. Come back after you've attempted the problem. So I have two masses, M1 and M2 are connected by light cables on the perimeters of two cylinders, radii R1 and R2. This is a really confusing picture. Okay, I don't like this perspective. The cylinders are rigid and connected to each other but are free to rotate without friction on the common axle. The moment of inertia, or rotational inertia, of the pair of cylinders is I equals 45, and then they have you R1, R2, and M1. Determine M2 such that the system will remain in equilibrium. Okay, so I'm going to draw sort of a horizontal view. I have a little disc, and I have M1 hanging off of it. And then I have kind of a bigger disc, and I have M2 hanging off of it. And the whole point of their picture is to basically say that the two are kind of and this is, it rotates around this point. This is R1, and this is R2. And they're basically saying they rotate together. So to be in equilibrium, the torques kind of have to be balanced with each other. Yeah, so it doesn't rotate. Yeah. So like we look at the torque from this guy. This guy's applying a torque M1 times R1 because the R vector is already perpendicular to the point of rotation to the point of where the rope is already perpendicular. And similar like this one, even though it doesn't look like on my picture, this R vector is already perpendicular to M2. So that has to equal to M2 R2. Now, they give us some numbers. I can solve for M2. M2 is just M1 R1 over R2, and they give you some numbers. M1 is 20 kilograms. R1 is 0.5 meters. And R2 is 1.5 meters. So this is like 1/3. That's 20 over 3. 20 over 3 kilograms. I'll leave it like that. I mean, what's that, like 6.667 kilograms or something like that? Okay. The mass M2 is removed and the system is released from rest. Determine the angular acceleration of the cylinders. Okay, so this thing is no longer there. So all I have is just this force causing a torque, which is a rotation. So the net torque then would be just simply equal to M1 R1. That's equal to 20 kilograms times 0.5 meters, and that's equal to 10 kilogram meters. Now that torque has to equal I alpha, and I is 45 kilogram meters squared. So when I do alpha, it's equal to kilogram meters. Sorry, I was just checking the units. So what have I? So kilograms, 1 over meter? No, that can't be right. Net torque. I'm missing a G. There should have been a mg here for all of this. I mean, the g's would have canceled that one. So I need to multiply by 9.8. So this should have been, I was doing a unit check, which is always a good thing to get, meters per second squared. So this would have been 98 kilograms meters squared per second squared is equal to 45 kilogram meters squared times alpha. And when I divide these two, 98 divided by 45, I get 2.18. And it's 1 over second squared, which we write as 2.18 radians per second squared, because the units of alpha is radians, turns out. Okay, determine the tension in the cable supporting M1. No, I didn't do this. I didn't do this setup right. Sorry. I should have done my free body diagram, and I didn't do my free body diagram, and that's really what messed me up here. Okay, let's do the free body diagram. The first part was right because the tensions were equal to M1G, but really, this tension, really my net torque is not equal to this. It's equal to the tension times R1, and that's equal to I alpha. Okay. So, but I don't know what the tension is. So for M1, I got to do a free body diagram on this guy. He has M1G going down, and he has T pulling up. And these are not equal to each other, because this guy is actually falling. Right? So the net force on this guy is M1G minus T, and that's equal to M1 times acceleration. So T is equal to M1 A minus G. Okay, I bring G minus A. And I'm going to plug that into here. So I get, so let me erase all of this stuff here. To make room. So really, when I put this together, I get T times R1. It's M1 R1 G minus A is equal to I alpha. So I wanted to find. Now, the problem is I don't know A or alpha. I know everything else but A or alpha. But A and alpha are related by this equation. A is equal to, A is equal to some R times alpha. Now, the R that I use is the one that's actually rotating at the end here, like this acceleration at this point. So it's R1. So it's R1 alpha. So I'm going to plug that into here. So I get M1 R1G. I'm going to distribute this M1 R1 times R1 alpha, right, is equal to I alpha. So I'm going to bring this over to here and factor out the R1. So I get M1 R1G is equal to I alpha plus M1 R1 squared alpha. So that's equal to alpha times I plus M1 R1 squared. And then now I can solve for alpha. So alpha is equal to M1 R1G divided by I plus M1 R1 squared. So M1 was 20 kilograms. R1 was 0.5 meters. G is 9.8 meters per second squared. I is 45 kilograms meters squared plus 20 kilograms times R1, which is 0.5 meters squared. Okay. So that is how you solve for alpha. So let me do this. 20 times 0.5 times 9.8 divided by 45 plus 20 divided by 4 is really 5. That's 50. Get 1.96 radians per second squared, which is the units of alpha. Okay. The tension, now we can solve. Tension was equal to M1 G minus A. That's equal to M1 G minus alpha R1. So that's equal to 20 kilograms times 9.8 meters per second squared minus 1.96 radians per second squared times 0.5 meters. Right, because A is equal to alpha R1, so I just do this. 1.96 times 0.5, 9.8 minus that, 8.82 times 20. I get 176.4 newtons. And then determine the linear speed of M1 at the time it has descended 1 meter. Well, this acceleration is, this this linear acceleration would be constant the whole time, because the torque's going to be constant this whole time. This tension and m1g, the forces aren't going to change. Doesn't matter where height is. So the linear acceleration is alpha r, and that's equal to 1.96 radians per second squared times 0.5 meters, and that's equal to 0.98 meters per second squared. So that's my linear acceleration. And then I want to just know its speed when it has descended 1 meter, so I use my kinematic equation. Delta x is equal to v naught t plus 1/2 at squared. This thing is released from rest, I assume. Actually, that's this I would require to know the time. So I'm going to use the other equation that relates velocity and acceleration and position. It's this one. V squared is equal to v naught squared plus 2a delta x. V naught squared, I believe, yeah, it's released from rest, so its initial velocity was 0, plus 2 times 0.98 meters per second squared times delta x of 1 meters. That's equal to 1.96 meters squared per second squared. So then v is equal to the square root of that, which is 1.4 meters per second. All right. Okay. I hope you found that helpful. I'll see you all in the next video. Thanks for watching the video, guys. Please leave a comment, like, or subscribe below to catch up more of the content. And see any links below. I offer free homework help on Twitch and Discord. See you guys in the next video.